Okay, let's get started. We're very happy to have Sahand here today to tell us something about anomalies and non-invertible symmetries on the lattice.
Okay, thank you very much for inviting me. It's an honor to give a seminar here online. So this talk will be based on these two papers that I put last year and this paper from a couple of months ago with Nati and Shuheng. And so I will talk about anomalies and non-invertible symmetries on the lattice. And so this subject, because it's a little bit about on the lattice, so if some people some people might not be familiar with this, so I encourage you to ask as many questions as possible. So please interrupt me whenever something was not clear. So I really prefer to have more questions and discussion during the talk.
Sounds good.
Okay, good, great. So okay, let me begin with the introduction. So the general idea is to use global symmetries to derive some dynamical constraint on some systems that are very hard to solve. So this system could be some strongly coupled lattice system that are relevant to condensed matter physics, or some strongly coupled quantum field theory that are relevant to high energy, string theory, and whatever. And so let me begin with two of the most important examples of these consequences. So the first example is actually an example from the lattice, and it's the famous LSM theorem by Lieb-Schultz-Mattis in 1961. So if you're not familiar with it, in the next few slides, I'm going to explain both of these. So what the LSM theorem is. And the example that perhaps more people are familiar with is in the continuum field theory, and is the Hooft anomaly matching conditions. And so before explaining what these two are, let me just tell you a teaser that actually there is a direct connection between these two examples. And as we will see, both of these constraints are associated with anomalies of global symmetries. But one is on the completely on the lattice, one is in the continuum. So let me start with the continuum and Hooft anomaly. So Hooft anomaly is defined as the obstruction to gauging a global symmetry. And so it's important because of the following two things. The first thing is that an anomaly, this Hooft anomaly, is an invariant under the RG, and this is known as the anomaly matching condition. And the second fact is anomaly is computable. It's something that even though if your system is strongly coupled, you could exactly compute it. I should say that you could in principle compute it, but usually in QFT setting, there is no automatic method to compute such anomalies, like non-perturbative anomalies. But in principle, it is computable. It's some exact quantity. And so this is for usual symmetries, and there is also the same story for non-invertible symmetries, and there is also a Hooft anomaly, which is defined as the obstruction to gauging, but the gauging is more subtle in the non-invertible symmetry case, because you have to say what you are gauging, you have to gauge the whole system, and there's a lot of discussion, and this is some subset of papers on this. And by the way, my list of references is not complete. I apologize for that. And for the complete list of references, please look at the papers that I mentioned. Okay, so this is the story of Hooft anomaly, which is in the continuum is defined as the obstruction to gauging. Now, the LSM anomaly, LSM type anomaly or theorem is on the lattice. Let me explain what this LSM is. So it starts with the original LSM theorem on the lattice. And the original LSM statement is the following. It tells you that if you have in 1D, so you have some Hilbert space, which is a tensor product of qubits, and let's say you have a spin a half chain. And it has some SO3 symmetry and lattice translation symmetry. So the original LSM theorem was about this particular Hamiltonian. Let's first forget about this deformation. It tells you that this Hamiltonian cannot have a unique gap ground state in the thermodynamic limit. But the story is more general. So the general statement is that as long as your Hamiltonian as long as the Hamiltonian preserves the SO3 symmetry and lattice translation symmetry, this fact is true. So this Hamiltonian has a lattice translation symmetry that basically shifts every Pauli matrix by one side. So sigma j, you have sigma j x, y, z. There are Pauli matrices at side j, and translation just shifts them by one side. And there is a SO3 symmetry, which is generated by these spin variables. And so the theorem is that if you write any Hamiltonian, so any deformation which respects the symmetry, whatever it is, this Hamiltonian cannot have a unique gap ground state. So this is the LSM theorem. And you see that this smells like an anomaly, because you say that just by knowing the symmetry of the problem, you could constrain the low energy behavior of the system. And so the modern perspective on this LSM theorem is that it should be viewed as a consequence of a mixed anomaly between lattice translation and the SO3 symmetry. But I should say that this is different from the way that we understand anomalies in the continuum. So in the continuum, anomaly is a property of a theory, but here is a property of the symmetry operators. So if I just give you the translation operator and the SO3 operator, the anomaly is the property of the operator, not the property of the Hamiltonian. And the consequence is that any Hamiltonian that you write down, which is invariant under the symmetry, would have this anomaly or consequence. So anomaly is a property of the operator on the lattice. It's a bit different. And in general, there is a type of things which are usually referred as to LSM type anomaly. So in general, LSM type anomaly of a symmetry operator UG, let's say they form some group G under multiplication. So LSM type anomaly of an operator is defined as a constraint which it imposes on any Hamiltonian that commutes with it. So in this case, we say that T and this operator, they have a mixed LSM type anomaly. And in principle, so this is different from Hooft anomaly, the way that I define it here. This was the way that was defined. Is there any question about this LSM theorem, LSM anomaly?
When you see this two symmetries has mixed anomaly, do you mean these two operators don't commute, or?
Okay, good. So the way that you will, so as I said, this is the modern point of view on it. So on the lattice, you will see some projective phases. So there are various ways to see that they have the mixed anomaly. So I will describe one of them. One is so the way that you will usually detect them, you in the continuum field theory, you have two symmetries. You put the defect for one, and you look at the action of the other one, and you see the other one is realized projectively. So there are some projective phases between them. And there is also a definition of Hooft anomaly. So one goal of this talk would be just to connect the definition of Hooft by abstraction to gauging to this anomaly.
I see.
But at this,
Sorry, I have a dumb question. I'm not familiar with LSM. I'm trying to reconcile this with just spontaneous symmetry breaking. If I have I have a family of vacua, and so I don't have a specific question. I was sort of hoping to generate one by the time I finish talking, but I don't seem to have quite met that deadline. Is there? Maybe I should just ask a big question. How is LSM related to spontaneous symmetry breaking? It sounds like they're talking about similar things.
yeah.
Existence or non-existence of unique gap ground states, symmetries that commute with Hamiltonian. What's the relationship there?
Good. So when I said it cannot have a unique gap ground state, so I should tell you what are the possibilities. So if you write any Hamiltonian with these symmetries, so the first one possibility that always exists is that this Hamiltonian in the thermodynamic limit is it has some gapless spectrum. So it's a gapless theory that has low-lying states. But the other possibility, if it's gapped, but when it's gapped, it has to necessarily break one of these symmetries spontaneously. But in one dimension, there is no spontaneous breaking of SO3. So the minimal condition is that the translation symmetry is spontaneously broken. So, and that's the case that often happens. So usually most of the Hamiltonian that you will write is gonna break translation symmetry spontaneously. So they would have like two vacua at least, for example, and they will be rated by lattice translation.
Okay.
But yeah, I will more explain on the interpretation of this anomaly, but the statement of the theorem is hopefully clear, right? Okay.
Yeah.
Right. Okay, so now the goal of this talk would be, so it would be two parts. The first part would be just about ordinary invertible symmetries. So the goal would be to find a macroscopic formula for the anomaly in 1+1 lattice Hamiltonian system, and then argue that it's the obstruction to gauging this anomaly. So in a way, we will show that LSM type anomalies are the same as Hooft anomalies for this case. Because even on the lattice, you could understand them as obstruction to gauging. There is a procedure to gauge them, which is satisfying. And for the non-invertible symmetry case, we don't have a general result like that. So I'm going to focus on a particular example of some exact non-invertible Kramers-Wannier duality type symmetry of the Ising chain and show that it has an LSM type anomaly, similar to what I said before. And the weaker statement, it would be that this LSM type anomaly in the continuum limit will correspond to some Hooft anomaly. But it would be some open question how to define the Hooft anomaly directly on the lattice for this non-invertible symmetries. But yeah, but also more. Okay, so yeah, this is the outline. So first part is about invertible symmetries, and the second part is non-invertible symmetries. So then let me begin with some background on this symmetry operators and defects, which will be important, this distinction on the lattice. So now I'm focusing on ordinary invertible symmetries. So what's the definition of a symmetry? So a definition of a symmetry, it's a unitary operator that commutes with the Hamiltonian. And one important property that we want to impose is that U kind of is local. It acts locally in the sense that it maps local operator to local operators. And this is very crucial. If our operator does not have this property, the story of Hooft anomaly and all of this don't hold. So one way to manifest this locality property is to represent the symmetries by topological defects. So the defects would be some modification of the system on some region of space, and because it's strictly some local modification, it will manifest this locality, and that would be one important tool for what I'm going to say. And the important property is that there is a one-to-one correspondence between symmetry operators and symmetry defects on the lattice. So this correspondence is very obvious in continuum Lorentz invariant theory because symmetry operator acts on space, and if you do a 90-degree rotation in Euclidean signature, it would be a defect. But in lattice Hamiltonian system, there is no Lorentz invariant. Even though there is no such Lorentz invariant, yet there is a one-to-one correspondence between symmetry operators and defects. And that one-to-one correspondence allows us to use defects as a definition of symmetry, and that makes it easier to compute anomalies. Stuff with it. So let me give you an example of what I mean exactly by topological defects in lattice system. So let me start with the easiest example, transpose fit Ising model. So what's the Hamiltonian? We have qubit per site. We have Pauli matrices X, Y, and Z at site J. So it has a Z2 symmetry. So the Z2 symmetry operator is a product of the Pauli X matrices that flips the spin. And for this operator, there is also a defect. And the defect corresponds to a local modification of the Hamiltonian. So if I put this defect on link 1, 2, it amounts to changing the sign behind this Z1, Z2 term. And that's a topological defect. So I just modify my system only locally. And in what sense is topological? So it's topological because actually I could move it by conjugating the system with a unitary operator. So let me define this object to be the defect Hamiltonian. So I'm calling my Z2 symmetry eta. So this is the defect for eta, and I have inserted on this link, j minus 1 comma j. And if you conjugate this Hamiltonian with xj, you will see that you will produce a minus sign on the zj term, and instead push the minus sign one side to the right. So I will get a defect on this link. So schematically, I write it like this, so this arrow is time, the vertical direction is time. So I start from a defect here, I apply a local unitary operator, and I move a defect by one side. And since these two systems are related by some similarity transformation, they are exactly the same physical system. They have the same spectrum and everything. So in that sense, this modification or this defect is topological. So that's the definition of a topological defect. And one notation that I'm using throughout this talk is this lambda eta j, which I call it the movement operator. So it moves the lambda defect, the eta defect from this side to this side. So move it one side to the right. This is the notation. In this case, it's just xj. So is this
Yeah. Sorry, just to be certain I understand, you're defining the defect to be topological by that property that H of one lattice, H of j plus 1 is the commutator, right. That's how you define
exactly.
Definition of topological.
Yeah. So if there exists a movement operator such that does this job, I will call it topological. And yeah, there is some relation between the operator and the defect. You could say, what's the relation between operator and defect? Why this topological defect correspond to this operator? So one hint of it is this piece, which is xj here, and this is also the product of xj. The point is that if you start from a defect here and you try to move it further apart, you move it by a sequence of unitary operators. And this sequence of unitary operator, which is the product of this movement operator, actually implements the action of the symmetry. So that's how the connection works. And so to find the expression, for the defect, you can conjugate your Hamiltonian with the symmetry which acts only on half of the space. And then at the end point, you will create this minus. I will explain this. But yeah, this is the connection. Good. Any other question? Okay. So now let me discuss this a little bit more general. So let's say I have a general group G. So again, I use this notation for a defect of G on this link. So this picture represents a defect Hamiltonian. And so for operator, we have a group multiplication law. And for the defect, this group multiplication law becomes a fusion rule. And the fusion means the following, that I could consider a Hamiltonian which now has two defects. So I modify the Hamiltonian around two sides. So I could put one defect G on this link, another defect H on this link. And I could try to fuse them. So the idea is that there exists a unitary operator, which I call it the fusion operator. That if I conjugate, so this arrow here is conjugation. That if I conjugate it, this defect Hamiltonian by this fusion operator, then I get a defect Hamiltonian for a single GH defect. And pictorially is this picture that I start with two defects, I conjugate the system with this unitary, and I found this defect at a later time. So in equation, I have this relation. And I should say the movement operator is a special case of the fusion operator. So if you set H to be 1, this is the same as moving G one side to the right. So here I'm picking some convention of always doing the fusion such that move everything to the right. This is some choice. So is the definition of this fusion operator clear?
Yeah.
All right, good. So now let me again, before going to the discussion of anomaly, let me again, I mentioned it briefly, but then mention it again, the relation between operators and defect. So if you start with the operator, you could let it act on half of the space. So let's say only acts on sites which are smaller than J. And if you conjugate Hamiltonian with it, you create a defect here. And going from defect to operator is this thing. So first you could start from site 1 and do an inverse of fusion. So fusion is that you could fuse G and G inverse to nothing, but the dagger is to create two defects, G inverse and G, out of the vacuum, out of the nothing. So you start from this. And then you have a G defect here. Let's say I have a periodic chain. And then you start moving it one side by one side. So you move it around the chain. And once it's here, then now you fuse these two together. So the initial condition would be just the untwisted Hamiltonian, and the final condition would be also the untwisted Hamiltonian. So at the end of the day, the product of all these operators will commute with your Hamiltonian, and that's the symmetry operator. So for the Ising case, all of these guys are just X Pauli matrices, and the symmetry operator would be the product of X's. And as I mentioned before, when you set H to be 1 of the fusion operator, this is just a movement operator. So this lambda G here is basically this guy that I defined before. Okay, good. So now let me, with this preparation now, let me go to the formula for the anomaly. So this is quite similar to the idea of computing the anomaly in the continuum. And the idea is to apply some kind of F moves between your defects to compute the anomaly. So the idea is to use the associativity of the structure of this defect. So you could start from a chain and insert 3 defects, G1, G2, G3. And now we could fuse them in 2 different order on the lattice. So on the left, I first fuse G2 and G3 via this unitary. And then I have to move G1 one side to the left, to the right. And then I will fuse, oops.
Oh,
And then I will fuse G1 and G2, G3 here to get this one. And I could also do it in the other order and first fuse G1, G2, and then fuse, G1, G2, and then fuse G2, G1 with G3. So note that there is this extra step that you usually wouldn't see in the continuum, because in the continuum, you could basically put all of them on top of each other. But there's this movement operator, which is important on the lattice, is not present in the continuum. The idea is that you do it in two different orders, and because the initial Hamiltonian and the final Hamiltonian on both sides are the same, the resulting thing should only differ by a phase, which depends on three group elements. And I claim that this is a local macroscopic formula for the anomaly. The nice thing about it is that is quite local, and you could do some explicit calculation to compute this anomaly. Basically, you just have to find this fusion operator, which are written in terms of Pauli matrices, and then you just multiply them and you find this fusion operator.
just for completeness, am I correct in thinking that F is going to obey some higher rules? If you have 4 group elements and you multiply them out in various ways, you're going to get some identity involving, a series of F's making some sort of pentagon identity.
Yeah, exactly.
So that's basically the lattice analog of an associator, or okay.
Yeah,
okay.
That's right. So F indeed is satisfies some pentagon identity, and we will see that this pentagon identity is a little bit modified on the lattice.
Okay.
Modification, but yeah, it's the same structure. But here it will contain a little bit more. I will explain in what sense. So, okay, this is exactly this slide. So I computed this function F, which is a function of 3 group elements, but this is subject to some constraint. And yeah, some constraint. So the first one is that F satisfy a modified pentagon or cocycle equation, which is this equation. So you see that this has 6 terms instead of 5. So this term on the right-hand side is usually absent in the continuum, and this is there because of the lattice. And actually, it would be a feature that this term is on the lattice. So because of this reason, there's this term on the right-hand side, we have a modified pentagon equation. The other thing is that I forgot to mention is that these fusion operators, they have some, sorry, this should be, okay, I changed the notation. This should be lambda J, G tensor H.
Okay, good.
So I forgot to change the notation here. This is just a fusion operator. So I forgot to say that the fusion operators are defined up to a phase, because the way I define them is by this equation. So if you multiply by a phase, they still satisfy this equation. So they are subject to some phase ambiguities, which actually in the continuum, these phase ambiguities correspond to adding local counterterm, these phase ambiguities. And so if you, let's say I multiply this lambda by this gamma, so gamma J are these phase ambiguities that I enter into the game. And if I multiply lambda, the fusion operator, by this gamma, my F transforms by this. So then this is an identification on the F. So this F and this F capture the same information. And there is a constraint that they satisfy. It's the pentagon equation, which is the analog of the Wess-Zumino consistency condition. So 1 and 2. But now let me restate 1 and 2 in terms of group cohomology, which might be more familiar to people. So actually, we could see that F defines some anomaly cocycles. So we could take this ratio of FG1, G2, G3 and divide it by FG1, G2, comma 1 and consider these 2 gadgets. And the interesting thing would be that if you consider this gadget, this would be a 2 cocycle and will satisfy the 2 cocycle condition. And if you take this ratio, this omega will satisfy the standard pentagon equation, meaning the 3 cocycle condition. So the F contains a 3 cocycle and also a 2 cocycle. So this is in some H3 group cohomology. This is in some H2 group cohomology. So it will turn out that omega is actually the Hooft anomaly in the symmetry G, which is some internal symmetry. And alpha would be the mixed anomaly between G and lattice translation symmetry. So in the case of LSM theorem, if you go and compute these two numbers, you will find that in the original LSM theorem of Heisenberg chain that I mentioned in the second slide, you will find out that omega is 0, so SO3 is free of anomaly, but alpha is non-zero. And there is a mixed anomaly between these two. And alpha is in H2. It will measure the projective representation of G. And indeed, in the Heisenberg chain, the SO3 is realized projectively on each side. And these two are correspond to each other.
So if I try to interpret this H2 plus as a SPT thing, like how should I understand it? How should I understand its connection to the translation?
To SPT, you mean SPT in the bulk? So you want to add a bulk and identify this anomaly?
If I say that I want to do some twisted gauging of the theory.
Uh-huh.
So, like, is this had some nice interpretation in terms of the mixed anomaly between this thing and translation?
Okay, so the claim is the following, that this omega is the obstruction to gauging G.
Yes.
And alpha is the obstruction to gauging G while preserving lattice translation symmetry. In that sense is the mixed anomaly. That there is no way to gauge G while making the translation symmetry operator be gauge invariant. There is no such a way to do the gauging such that the translation symmetry operator remains gauge invariant.
I see. Yes.
Okay, so I guess I prepared too much. So let me explain this gauging, but I will be quick on this gauging. So if there are some questions, I could explain. So I want to very shortly argue that actually these two numbers are obstruction to gauging on the lattice. So how do we do the gauging on the lattice? So the idea is that usually you have to add gauge fields on the links and impose Gauss law. So gauging consists of two steps. Let me do the first step, adding dynamical gauge fields. But these are not really fields, they are like spin variables that lives on the link. So the first step would be to enlarge the Hilbert space by adding, so let's G to be finite. Let's take G to be finite. So I add G-dimensional Hilbert spaces on each link. These are the analog of the gauge fields. And once I've enlarged it, so basically I define this H tilde is the enlarged Hilbert space, is the sum over all of these things. So I'm adding these qubits on each link. And then the Hamiltonian of this extended system, I take it to be this. So what is this term here? This means that I insert defects on all of the links. So I insert G1 defect on this link, I insert G2 defect on this link, and so on. And I insert the GL defect on the last link. So this is a defect Hamiltonian for all of these defects. And we know that in the gauging, you have to add gauge fields and sum over all of them. So I'm summing over all possible configuration of the defects, or aka background gauge fields. Then there is a part, so this is a part that acts on sides. And there is a part that acts on links. Basically here is a projection operator that keeps track of the gauge field variables. So this is the extended Hilbert space. And then I could also extend my fusion operators. So I have a fusion operators. And then I could add these pieces which acts on the links, which basically keep track of the defects. It tells me that a defect G and H fuse to GH. So this is lambda tilde. So the nice thing about this is that before the fusion operator, we're conjugating two different defect Hamiltonian with each other. But in this extended system, the fusion operator actually commutes with the Hamiltonian. So it smells like a local symmetry or like a gauge symmetry. It's almost like a gauge symmetry because I have some local operator that commutes with my Hamiltonian. But this is not invertible. So the second step is just to make this invertible, to obey the same multiplication law. And the idea is to define this guy. So I just basically have to sum over all of them. And diagrammatically is easier to think about this. So I sum over all A and B. So I take A and B, fuse them to AB, and then split them, the inverse of the fusion, into AG minus GB. And because this lambda tilde commutes with the Hamiltonian, this G is also commutes with the Hamiltonian. But the nice thing about G is that G actually is a representation of the symmetry, is a local G symmetry. If you multiply Gj with Gh, you get Ggh. So H tilde has a local G symmetry. So to impose the Gauss law, basically we have to set G to 1 or take this projection operator and set it to 1. So this is the second step, which is imposing Gauss law. And the nice thing here would be that with a little bit of easy algebra, you could show that it would be only consistent. So first of all, it would be only consistent to do the gauging if Gauss law at different sites commute with each other. Because the Gauss law, they should mutually commute with each other. And you could see that the Gauss law at site J commutes with the Gauss law at site J plus 1, if and only if this F vanishes. This F is trivial. So you could directly see that this F is actually the Hooft anomaly. It's cohomology class because you might be able to redefine it with some phases, as I explained, to cancel it. But anyway, so this will show that this is the obstruction to gauging in the sense that the Gauss law will commute if it's 1. But in this sense, we have shown that this LSM type anomaly is actually the Hooft anomaly. Okay. Any question? Okay, good. So now let me go to the non-invertible symmetry discussion. All right. Okay, so let me start with again with the Ising chain. But I have set the coupling to be the critical coupling. So before I had a coupling G here, but here I've set it to 1. Let's say discuss this critical Ising Hamiltonian again, and it has some standard symmetry. So you have a standard Z2 symmetry eta, which is the product of xj's, and it has a lattice translation symmetry T, which shifts any qubit by one side to the right. But on top of that, it's also invariant under the Kramers-Wannier transformation. What's a Kramers-Wannier transformation? So you could take xj and send it to zjj, to 2z's, or take 2z's and send them to x. And you could check easily that this Hamiltonian is invariant under this transformation, this duality transformation. So the question is that, what is this transformation? Can we think of this transformation as a non-invertible symmetry or non-invertible symmetry or not? In what sense is a non-invertible symmetry? So for usually unitary symmetry, you cannot write any transformation and say it is a symmetry. You have to make sure that is an automorphism of your algebra that is implemented by some unitary operator. For example, the first thing that you could check is that there is no way that this transformation is generated by a unitary operator. So let's assume for a second that there is a unitary operator that implements this transformation. Okay, so we take this and it sends to this. So take the chain to be periodic, and let me take the product over J for Zj minus 1 Zj. If I take the product over all J's, so this Zj minus J Zj, they all cancel each other telescopically, right? If I take all of them. But this rule tells me that it should be mapped to a product of x's, which is non-trivial. So a unitary operator cannot sense identity to something non-trivial. So immediately we see that there is no unitary operator that could implement this transformation. So one question is that, what is the consistency condition? Can we just write down any transformation and impose a non-invertible symmetry or not? So that's, I think, is still some interesting question to study. But for this particular example, the claim is that this Kramers-Wannier transformation is implemented by a non-invertible symmetry operator that I define it by D, and is implemented in this following sense. So D, there is no dagger, sorry, there is no inverse for D, but still I could still consider this intertwining kind of action, that I write dxj, so I try to push D through xj, and the claim is that it becomes Zj minus 1 Zj. Yeah. So this is the claim that I want to show.
And I can still define the dagger as the reverse orientation of this operator, I guess.
Okay, so yeah, D dagger, you could, because it's an operator, you could just define it as the dagger.
I see.
And There would be later, I will discuss the notion of dual and this, yeah, the orientation reversal, and the story is works a little bit differently from the way it works in the continuum. So I'll discuss this dual, which I think is related to your comment about orientation reversal.
I see.
So one thing to note is that if you square the Kramers-Wannier transformation, it squares to a translation. So if you start with xj, you do it twice, you get xj minus 1. So this D is like a non-invertible lattice translation symmetry. And I should say that this transformation, it's not an automorphism of the algebra, but is an automorphism on the space of Z2 invariant operators. So this D has a nice action on Z2 invariant operators. So my Z2 symmetry is just product of xj. So one Zj is not Z2 invariant, but two Z's are Z2 invariant. And this Kramers-Wannier have a nice action only on Z2 invariant operators. Okay, so now I want to prove this claim that this D exists. I want to basically construct this D for you on a periodic chain. So the idea is to use defects. So the interesting observation is that the Ising Hamiltonian is actually self-dual under gauging its Z2 symmetry eta. And that's basically the modern point of view on the Kramers-Wannier duality. So the Kramers-Wannier duality in more modern terms, you should understand it as that it implements gauging of a Z2 symmetry. And the gauging is, again, you add gauge fields on the links. There's some systematic procedure that I don't have to review it here, that you, again, add gauge fields on the links, impose Gauss law, and then you do a change of variable to write down the gauge field in terms of the original variable. And that gives you a transformation. You begin with some Hamiltonian and you find the gauged Hamiltonian. And you can check that the Ising Hamiltonian at the critical coupling, when the coefficient behind x and zz terms are the same, it's actually self-dual under gauging. So the gauging will exchange the x terms with the zz terms, the same as Kramers-Wannier transformation. So the idea is that the Kramers-Wannier transformation is gauging. So to be able to find the defect, I have to do this transformation on half of the space. So the idea is to do the gauging on half of the space. So if I do this procedure of half gauging, so I introduce gauge fields to live only on half of the space, and then repeat all of the steps. I introduce gauge field on half of the space, I impose the Gauss law. Then by doing this procedure, I could find an expression for the defect Hamiltonian. So I didn't have time to do it, but if you do that, you will find this defect Hamiltonian. And here I'm using the curly D notation. The curly D is for the defect, and this text is for the operator, but these are related. So at the end of the day, you will find this expression for the defect Hamiltonian. You see that away from this link 1, 2, this is the standard one, but it differs. So Z1, Z2 terms become Z1, X2, and there's no X2 term. So it has one less terms than the original Hamiltonian. So this is the expression. This has been written before, but you could also derive it from half gauging, which is the new derivation. So again, the point is that this defect is topological in the sense that there is a movement operator. There is an operator that you could conjugate the defect Hamiltonian when it's on this link and shift it by one side to the right. So this is lambda D is the movement operator, and the expression is in terms of these two things. So this is known as the Hadamard gate, is just this guy here, and this is the CZ gate, but this is some explicit expression in terms of x and z's. By just easy algebra, you could basically just check, do this conjugation and check that the defect, you will move the defect one side to the right. Okay, so this is how you derive the defect. So to derive the operator, I have to also know what is the dual defect, what is the fusion. So let me do the fusion of this non-invertible defect. So the idea is similar to the invertible case, is that I want to start with a Hamiltonian that has two defects. I guess I have a typo here, sorry. This should be L. So this should be L minus 1L, and this should be L comma 1. Yeah, I apologize for that. So you put two defects on these two adjacent links, And the idea is to, again, use some unitary to simplify the Hamiltonian that has two defects to be able to fuse them. And the claim is that there is some unitary that I will describe it in the next slide, that if you conjugate this Hamiltonian for two defects, so two of these guys here, then you will find this Hamiltonian, which I claim is quite simple Hamiltonian. So let me describe what this Hamiltonian is in the second line. So you see, in this second line, site, so I started with a periodic chain of L sites. That was the initial thing, and I put the two defect. So in the second line, the qubit at site L is almost decoupled from the system. The qubit L only appears as a coefficient of this term. So this term here is just a standard Ising Hamiltonian and does not have the qubit L in it. So what we are seeing here is a Hamiltonian that commutes with ZL. So basically, we could write this Hamiltonian in a block diagonal form. We could diagonalize it with respect to ZL. So ZL has two eigenstates, the qubit 0 and qubit 1, up and down. And if you write it in this block diagonal form, it has this part and this part. But what is this part? This is basically the Hamiltonian for an Ising chain, but with L-1 sites, where you basically throw away site L and you make site 1 and L-1 to be neighbor to each other. So this is just the standard Ising Hamiltonian with L-1 site, because the value of ZL is +1. And here is again the standard Ising Hamiltonian, but there is a minus sign here. So it means that it has a single eta defect on it. And so here, this Hamiltonian, which has less sites, I want to interpret it as a defect, which I call it T inverse, sorry, T minus. So then this expression here is interpreted as this fusion rule, that if you fuse two D defects, you get a superposition of a T inverse defect and a T inverse eta defect. And yet another point is that this T inverse defect is a lattice translation defect. So let me explain why. So T inverse defect amounts to just removing a site. And the claim is that removing a site first is a topological defect, because it doesn't matter if you remove site 1 from your system or site 5 from your system. At the end of the day, these two systems are related by relabeling what you call site number 1 and what you call site number 2. So you just remove one site, it doesn't matter. So it's topological. And the other thing is that this correspond to a lattice translation defect. And there's various ways to see that, because once you increase the system size, the clearest way is to remove a site and try to move this defect to the right. And this corresponds to some relabeling, which are some product of swap operators. And if you do this on a region, you will find out that you reconstruct the action of the translation symmetry. So in the paper, we give 3 arguments and show it in 3 different ways why this removing a site corresponds to a translation symmetry defect. So at the end of the day, we find this fusion rule, that D times D correspond to these 2 terms. So is this calculation here, is this clear? Good, great.
So in terms of the operators, I have exactly the same formula here.
Operator for lambda?
No, for just the fusion rule here. I don't use defect, but I use operators.
Oh, great. Yeah.
So formula, or it was something different?
Yeah, great. So if you do it for the operators, you will exactly find the same thing. So you will find, I will discuss it later, but you will find D times D. This would be the translation operator, and this would be the eta operator.
Great. Okay.
I use this notation so that the fusion of defect exactly parallel for the fusion of operators. But yet I haven't constructed the operator. The idea is to first use this to construct the operators and then show that they satisfy the same fusion rule. Good. So now let me discuss this operator a little bit more. So before we saw that there are 2 fusion channels. fusion to this guy or that guy. So now I want to only consider, let's say I'm only interested to this fusion channel. So this operator here is unitary. So I want to consider a non-invertible fusion operator. So let's say I'm only interested in the fusion channel that DD goes to T inverse. So I take this unitary operator and multiply it by this bra of L, of side L. And by the way, this is the explicit form of this unitary. It's some Hadamard gate that I showed before and some CZ gate. So I define this non-invertible fusion operator, which implements the fusion of DD to T inverse by this one. And schematically write it like this. And since this is not invertible anymore, so I cannot use this inverse, but then the equations, the fusion equations become this. So before this guy was on the left-hand side, it's inverse. But I don't have its inverse, but still I could use this intertwining relation. The idea is that if you push the fusion operator pass through the Hamiltonian, you will implement the fusion of DD to T inverse. So this is a definition of the fusion operator for non-invertible defect. And I could use this to create the operator. Okay. Any question here? Okay. One last piece of technical thing is about the dual defect. So usual for ordinary invertible symmetries, we have a notion of inverse, and this notion of inverse becomes the notion of dual for defect. So basically, I want to find the dual defect D star such that DD star contains the identity on the right-hand side. And you see, it's quite easy to construct this. Given this operator, so this defect was corresponding to removing a site. And this defect is invertible. It has an inverse. The inverse of this defect is adding a site, right? Removing a site is a topological defect. Adding a site is also a topological defect. So adding a site, I just indicated by T plus. And if you bring this guy to the left-hand side, you will find that D star, which is defined this, is 1 plus eta. So the idea is that D star is the dual defect, and it corresponds to D tensor T plus. So it's D, but you also have to add a side to your system. So in some sense, it has some lattice quantum dimension 2. So there is a notion of quantum dimension in the continuum, but the notion of lattice quantum dimension is basically the local change in the size of the Hilbert space. So the defect D has lattice quantum dimension 1 because you don't have to touch the Hilbert space. But the D star defect, you have to add a site, and a site is a 2-dimensional qubit. So you have to increase the dimensionality of Hilbert space by 2. So it has a lattice quantum dimension 2. And they both multiply to 2, and the square root of 2 is the continuum quantum dimension. So I will explain some relation between those two. Anyway, so this is the dual defect. And you see that this is different from the continuum, because in the continuum, dual defect is orientation reversal. Here, D is the same as its orientation reversal, but it's not self-dual. Even though it's the same as its orientation reversal, it's not self-dual, because D times D does not contain the identity. Okay. And now there's also, you could also consider the explicit fusion operators that do these two fusion. So there are two fusion channels, DD star to 1 and DD star to eta. Schematically, there are these two relations. And these two fusion operators satisfy these two relations. Okay. So now, equipped with this fusion operator, now I could easily construct a symmetry operator on a periodic chain. So the idea is very similar to this here. Creating a pair of defects, moving them around the chain, and then fusing them. So using this idea, so using the fusion operator and the movement operator, we could construct the non-invertible operator as this formula. So this term on the right-hand side correspond to creating a pair of D star and D defect. But unlike the case of invertible symmetry, this is no longer unitary because it has this bra and ket in it. So this is non-unitary. So you create a D star and D. And once you have a D, you just try to move it around the chain. So these are all implemented by unitary operators. So these are all unitaries. And once you have it here, now you could fuse D and D star with this local operator. So all of these are unitaries, but because these two pieces are non-unitary, you will find out, you will leave with, left with some non-invertible operator. And you could simplify this expression and have a very elementary expression in terms of just X and Z Pauli matrices. So you see the sequence of unitary operators, and at the end of the day, there is only a single projection operator, which makes it non-invertible, because all of these are unitaries. So basically, this is a derivation of how to derive this non-invertible operator from the defect by their fusion. So I had to define the dual defect and all of these things. And this is a question that I was asked before, and this operator satisfied the following fusion algebra. So this D squared is T inverse plus eta T inverse, you see, which is quite parallel to this relation. So T inverse is a translation operator, and tau inverse, tau minus is a translation defect. And there's also this fusion algebra relation that there's also, these are also true for the defects that I didn't describe before. And the analog of D star being DT plus is the fact that D dagger is TD. So D is not self-adjoint operator. It's associated to the fact that D is not self-dual, the lattice. So the final point is that this operator, this non-invertible operator D, has an LSM type anomaly, in the sense that we could prove a theorem, which is that any Hamiltonian that commutes with D must either be gapless or spontaneously break D with multiple of 3 ground states. So any Hamiltonian which is invariant under D cannot have a unique gap ground state. Like quite similar to the LSM type, to the original LSM theories. And so now I want to argue for this LSM type anomaly in D, if there are no questions in this slide.
So is there any nice, like physical intuition of some numbers in this operator expression, like this 1/8 in exponential?
Oh, some explanation for this 8?
Yeah, right. Is there any, I don't know, is it just some technical result, or is there some physics behind this number?
There are, so in the last slide, so it has some remnant. Okay, it's related to the fact that for the Ising Hamiltonian case, it flows to Ising CFD, and in Ising CFD there is a 1/16 of the conformal dimension. So there is some relation to that.
I see.
But it is very specific to the Hamiltonian.
I see. Okay.
The other answer would be just these phases are there so that in this equation you don't get any phases.
Yeah, I see.
The procedure of the defect only fixes D up to an overall normalization, and this normalization is chosen such that satisfy these relations.
Thanks.
Yeah, thanks for the question. Okay, so now let me argue for this LSM type anomaly. So the first thing to note that I mentioned, I think I mentioned it before, is that D implements the gauging of the Z2 symmetry eta. In the following sense, that if you start with Hamiltonian H, which is invariant under Z2 symmetry eta, and if you try to push D pass through H, you find a gauged Hamiltonian. So this is a true relation. That this is a Hamiltonian for H, and this is a gauge version. So D implements gauging, the same way that Kramers-Wannier implements gauging. So therefore, any Hamiltonian that a Hamiltonian commutes with D if and only if it is self-dual under gauging its Z2 symmetry eta, right? So being symmetric under D is the same as being self-dual under gauging Z2. So now, let me tell you some fact to be able to argue for the LSM type anomaly. The first fact is that there are only two 1+1 the Z2 symmetric gapped phases. So there are only two, gapped phases in 1+1 dimension that has a Z2 symmetry. You either have a trivial phase, so you have the so-called symmetry preserving phase, which corresponds to a trivial TQFT with partition function equal 1. So that's a trivial phase with a Z2 symmetry. Or you have a symmetry breaking phase. So symmetry breaking phase, basically you have two vacuo, two super selection sectors, and they're exchanged by the action of the Z2. And from the TQFT point of view, it's described by Z2 gauge theory in 1+1 dimension, with partition function is 2 on any genus G-Riemann surface up to Euler character. So there's only these two possibilities for a gap phase. The second point is that these two options are actually exchanged under gauging Z2. So if you start with a symmetry preserving phase and you gauge Z2, you go to a symmetry breaking phase and vice versa. And we also have a lattice. So these are well known in the continuum. And we also have arguments on the lattice based on this operator D, that why D exchanges the order phase with the disorder phase. Right? Okay. So now, given these two facts, it's quite clear that a self-dual gapped phase must have multiple of 3 superselection sector. Because, okay, it's either gapless, but let's assume it's not gapless and it's gapped. So gapless is always a scenario. And now if it's gapped, you take a superselection sector. If it's symmetry breaking, if it's symmetry preserving, you act with D, you get a symmetry breaking phase. So the number of symmetry breaking superselection sectors are the same as the number of symmetry preserving one. So you have A number of symmetry breaking and A number of symmetry preserving. So at the end of the day, the number of ground state or superselection sectors should be multiple of 3. That's the LSM type constraint that we prove. So now let me comment on the continuum limit of this LSM type anomaly. So, sorry. As I said, the non-invertible symmetry has an LSM type anomaly. And the claim is that it becomes a 't Hooft anomaly in the continuum limit. So what do I mean? So the continuum limit depends on the choice of the Hamiltonian. So I emphasize again, the LSM type anomaly is a property of the operator, symmetry operator itself. But the continuum limit depends on the dynamics and the Hamiltonian. So let's choose an example. Let's choose the Ising Hamiltonian case, where D is a symmetry of it. And the claim is that if you take the continuum limit, you get this expression, this relation between the lattice operators and the continuum operators. So the continuum limit of Ising Hamiltonian is just the Ising CFD. And we know that Ising CFD has a non-invertible symmetry, which has this, duality line, which forms this Tambara-Yamagami fusion category with this fusion rule. And the idea is that there is the following relation between this non-invertible operator on the lattice and the continuum. So basically, D becomes N, which is the non-invertible symmetry of the continuum, times e to the 2 pi IP over 2L, where P is the lattice momentum, which is defined by this relation. Basically, lattice translation in the continuum becomes lattice momentum divided by L for a system with L sides. So this is an exact relation on the low-lying states. And it's well known that the non-invertible symmetry of the Ising CFD has a 't Hooft anomaly in the sense that it cannot be gauged. There is an obstruction to gauging the whole thing. The idea is that this LSM type anomaly becomes the anomaly in the Tambara-Yamagami fusion category. So now let me mention 2 important points here. That our symmetry on the lattice is not the Tambara-Yamagami fusion category, because our lattice non-invertible symmetry has a different fusion rule than this, right? This eta is self-dual, but for us, eta is not self-dual. It mixes with translation. So the Ty Z2 plus symmetry does not exist on the lattice, and it should be interpreted as an eminent symmetry from the point of view of this paper. It emanates from this symmetry D. So there is no way to break there is no way to break N while preserving D. So in that sense, it's not emergent, it's eminent. But the point is that our symmetry on the lattice is not described by fusion category and is not this fusion category. To make this point even more clear, we claim that there are other choices of the Hamiltonian where in the continuum limit, the eminent symmetry is described by T by Z2 minus instead of T by Z2 plus. So this Tambari-Yamagami have a twofold classification. There's this Frobenius short indicator, which you have to determine. For Ising CFT is +1, but there are other systems where Frobenius short indicator is -1. And the point is that this Frobenius short indicator is not well defined on the lattice. And the main reason is because this D is not self-dual. The Frobenius short indicator is only well defined for self-dual point. So there are deformation that we discuss in appendices that you could go between these two cases. So that was the first point that is not a fusion category. So now, lastly, let me mention a consequence of this anomaly. So because there is this LSM type anomaly, so any deformation, you know, as I said, there are two scenarios, either gapless or has 3 super selection sectors. So now let me tell you some numeric results about some phase diagram that confirm this prediction. So we could take deformations of the Ising Hamiltonian. So let me turn on these two deformations, lambda and G. So first, G is not very interesting because G, the deformation G breaks the non-invertible symmetry. So let's say I'm only interested in G equals 1. So this phase diagram here, the horizontal axis is G and vertical axis is lambda. So lambda is kind of this tree interaction, tree next nearest neighbor interaction that I add. So the important point is that this lambda deformation preserves the non-invertible symmetry D. And G breaks it. So only G equals 1 has this symmetry. And so the transition for G is just a symmetry breaking order and disorder transition. So it's not interesting. So let's focus only on G equals 1. Because, you know, G less than 1 is symmetry breaking phase and G bigger than 1 is symmetry breaking phase. It's completely understood. Now let's focus on G equals 1 and study this lambda deformation. So the point is that since lambda preserves the non-invertible symmetry, there is a constraint on the low energy physics. So at lambda equals 0, we have the Ising CFT. But it turns out that if you turn on lambda up to this critical value, which is 0.43, you still are in the Ising CFT universality class. And at this point, there is a critical point that you go to the tri-critical Ising CFT. And if you go above that, you go to a gapped phase with 3 vacua. And this has been numerically checked. And I should say that this actually, it's an analog of some famous RG flow in the continuum, but not from the Ising CFT, but if you start from tri-critical Ising CFT. So tri-critical Ising CFT has a deformation that preserves this Tambara-Yamagami symmetry. For one sign of the deformation, the theory falls to Ising CFT, and for one deformation, it falls to a gapped phase with 3 vacua. So this is something which is integrable and has been solved by Zamolodchikov in the continuum. And here we are just seeing a kind of lattice analog of it. But here, because we are not starting with a CFT, there is no notion of going up or down along the RG flow. So we could directly, you know, starting from the Ising and goes to the tri-critical on the lattice. And actually, these 3 vacua matches with our prediction of this LSM type anomaly. Okay, so now let me end with some open questions. Thank you for your attention.
Any questions? So, yeah, I have one question.
Yeah.
So in the continuum case, right, we know that the Kramers-Wannier line or this non-invertible symmetry can be think of as a result of the Bostonization, right? Like
Yes.
I have this anomaly between -1 to the F, -1 to the FL. Gauging -1 to the F, -1 to the FL is promoted to the Kramers-Wannier side.
Yeah.
Can I see this from the Majorana chain? Like if I have some fermionic chain, then there are some mixed anomaly between some.
Yeah, exactly.
-1 to the FL on lattice, right?
Yeah, so exactly. So in the paper before us, so the paper by Shuheng and Nati, they exactly study what you described. So they start from the Majorana chain, they study the symmetry, and they do exact Bostonization on the lattice, which is just a Jordan-Wigner transformation. And actually on the lattice side, so in the continuum, we have -1 to the FL, which is a Z with the mixed anomaly. But on the lattice, it's realized as a translation symmetry. So there is no way to realize that chiral Z2 symmetry as an internal symmetry on spin chain. But what is happening is that the Ising the Majorana chain has a Majorana translation symmetry, and that Majorana translation symmetry in the continuum becomes a Z2 symmetry. So there is a mixed anomaly between Majorana translation and -1 to the F. And after doing Jordan-Wigner, it becomes this non-invertible lattice translation symmetry.
Oh, I see. So, okay. So it seems like everything is connected to this lattice translation, no matter it's fermionic or bosonic. I see.
Yeah, exactly.
I see. Okay. Thanks.
Yeah, thanks for the question.
Yeah, another question, I guess. Yeah, right. So if I consider some other exotic lattice model, like some fractonic base, based on your early statement, I guess there's no way I can define locality for those symmetries. Like the subsystem symmetry, usually speaking, they're not topological, right?
So we could define a locality. So the subsystem would be is just topological in certain direction, not in all direction. So I think there are also papers on this, some subsystem, even non-invertible symmetries by
Oh, I see. You mean by
and others.
right?
Yeah. So they study these defects, but these defects are only topological in certain direction.
I see. So I can still right on top of the defect on lattice, etc. I see. Okay. Thank you.
Yeah, no problem.
I have to go teach, but I wanted to say it was a very nice talk. Thank you for speaking here, and I've got to run, but it's not, I'd love to stay and chat more, but I've got to get out of here.
Thank you.
So, yeah. So if there's no question, I think we can thank Sahand again.
Yeah.
Thank you. It's a very nice talk.
Okay, thank you. Yeah.
I remember we met like several times before, right? I don't quite remember. I guess I was in your. I guess I was in your thesis defense.
Yeah.
In 2022, I guess.
Yeah, we met at Stony Brook a couple of times. Yeah.
Yes, right, and also last year's annual meeting. I think we don't talk to each other, but I remember I met you several times. I mean, yes.
Yeah. No, I remember. Yeah.
You've been doing great, interesting things.
Thank you.
Yeah, I think. Let me see. Do I? Okay, start recording.